Hey everyone, and welcome to another deep dive. Today we're going inside those intricate systems that make modern aviation possible, aviation electronics.
Really diving deep into the instruments and gauges that pilots rely on.
Exactly. And we've got a great source to guide us, something with a real hands-on perspective, an Airframe electronics homework assignment.
Should give us a good grasp on the nuts and bolts, so to speak.
Pun intended.
Maybe.
Well, get ready, folks. We're about to find out what makes these Borden tubes tick, why standard day is anything BOT standard, and how those colorful markings on aircraft instruments are like a secret language for pilots. You ready to jump in?
Born ready. Let's do it.
All right, let's tackle these Borden tubes first. I'll be honest, the name doesn't exactly scream essential aviation component. Can you give us a quick rundown of what they are and why they matter so much in the world of pressure gauges?
Sure, imagine a spring, right? But instead of a coil of wire, it's a tube, specially shaped tube. That's your Borden tube.
Okay, I'm picturing it. So what makes this tube so special when it comes to pressure?
Well, when pressure builds up inside this tube, it tries to straighten itself out. And the more the pressure increases, the more it uncoils. That straightening motion, that's the key.
How so?
That motion, that's what drives the needle on your pressure gauge. More pressure, more straightening, higher reading on the gauge.
It's amazing how something so simple can be the backbone of something so important. So we're talking pressure gauges. Where might we encounter this ingenious little tube in our everyday lives?
Oh, all over the place. Think about when you check your tire pressure, that gauge you use, Borden tube. Or maybe you've used a pressure cooker. Same principle at work.
Wow, I never would have guessed my tire gauge and a pressure cooker had something in common with keeping a plane in the air.
Hmm.
But speaking of planes, that's where we really want to understand this Borden tube business.
Mm.
What are some of the key roles it plays in keeping those aircraft up and running?
You hit the nail on the head. It's all about keeping things running smoothly, literally. In aircraft, you'll find them measuring hydraulic pressure. That's vital for controlling things like the flaps, landing gear, brakes, anything that needs a lot of force to move smoothly.
Sounds pretty critical to me. And I'm guessing fuel pressure is another big one?
You bet. Keeping tabs on fuel pressure is kind of essential if you want to stay airborne.
That's putting it mildly. I can't imagine anything more nerve-wracking than a fuel gauge going haywire mid-flight. Talk about a different kind of pressure.
No kidding.
You know, that actually reminds me, our homework mentioned something called standard day. And I know every day can feel like a roller coaster ride sometimes, but in aviation, it seems like they take standardization to a whole new level. Why is having this standardized baseline so crucial for everything they do up in the air?
It's all about having a common reference point, a universal reset button for everything related to flying. It defines a specific set of atmospheric conditions, 15 degrees Celsius, that's about 59 Fahrenheit, and 29.92 inches of mercury for air pressure, all measured at sea level.
So it's like saying, okay, everyone, let's make sure we're all speaking the same language when it comes to our instruments and calculations.
Precisely. Pilots, mechanics, engineers, they all use this baseline for calibrating instruments, predicting how an aircraft will perform under different conditions, even just communicating with each other clearly.
Sounds like it prevents a lot of potentially dangerous misunderstandings. Now, I also noticed the term pressure altitude right alongside standard day. What exactly is pressure altitude, and why is it something an A&P mechanic needs to wrap their head around?
Think of it this way. Pressure altitude is all about understanding how air pressure changes as you go higher, and how those changes affect how an aircraft performs. It's basically the altitude you would read if you were at standard sea level pressure. Remember those 29.92 inches of mercury?
Okay, I'm with you.
Now here's the thing. Even if you're physically at a certain altitude, let's say 5,000 feet, your pressure altitude might be higher or lower. It all depends on the actual atmospheric pressure that day.
Hold on, so I could be looking out the window at 5,000 feet, but my instruments are telling me something different? That's kind of wild.
It is, but understanding that difference, that's what's crucial for A&P mechanics. Let's say you have a plane with engine trouble at a certain altitude. A mechanic could use pressure altitude to simulate different altitudes on the ground in a controlled environment, helps them figure out if the problem is related to the altitude or something else.
That's incredible. So it's like they're bringing this guy down to earth for troubleshooting. It's like they always say, don't assume, check your instruments. And speaking of instruments, we've covered pressure, but something tells me there's another vital measurement pilots are keeping a close eye on: temperature.
You got it. Just like with pressure, pilots need to know what's happening temperature-wise, both inside and outside the aircraft.
Absolutely. And our homework gave us two main methods for measuring temperature: resistance-based methods and thermocouples. Could you break those down for us? What's the difference?
So resistance-based sensors, specifically a type called RTD's resistance temperature detectors. Basically, the electrical resistance of the metal in the sensor changes as the temperature changes. Measure the resistance, and you've got your temperature.
Makes sense. So how do thermocouples compare?
They're a bit different. Instead of just one metal, we're talking about two different types of metal wires joined together. And when the temperature at that junction changes, it actually creates a voltage.
Whoa, so it's using a bit of electrical magic to measure heat. That's pretty cool.
It is. And just like those Borden tubes we talked about, thermocouples are valued for being simple and reliable.
Speaking of reliability, our homework mentioned that different engines use different types of thermocouples. Chromel-Alumel for jets, iron constantan for piston engines. Why the need for different metals?
Well, think about the extreme temperatures involved. Jet engines. Those things get HOT, thousands of degrees hot. Chromel-Alumel thermocouples are built tough, designed to handle that intense heat and still give accurate readings.
I can only imagine. So piston engines run a bit cooler.
Relatively speaking, yes. Still hot, but those iron constantan thermocouples, they're perfect for that temperature range. Using the wrong thermocouple for the engine would be like, well, trying to measure a volcano's temperature with a meat thermometer. Not very effective.
And probably a good way to end up with a melted thermometer. Which makes me think you wouldn't want someone messing around with those thermocouple leads, would you? Like adjusting the length or anything?
Definitely not a DIY project. Even a small change to the thermocouple leads can really mess with the accuracy of the temperature readings. We're talking potential engine damage if things get out of whack.
Wow, so it's not just the temperature gauge being off by a few degrees. It could have some serious knock-on effects.
You got it. Accurate temperature readings are vital for keeping those engines running smoothly and safely.
This whole discussion about how instruments talk to each other has me thinking about something else from our homework synchro systems. The name sounds like something straight out of a sci-fi movie, but something tells me they're a bit more grounded than that.
They might sound futuristic, but synchro systems are actually pretty simple. Think about a compass in the cockpit. That compass needs to tell other instruments what the heading is, right? Otherwise, it's not much use to anyone but the compass needle.
Makes sense. So how does the compass talk to the other instruments?
Synchro systems are the link. They use electrical signals to transmit the angular position, the direction the compass is pointing to, instruments like the heading indicator.
Ah, so it's like an invisible handshake between instruments, making sure everyone's working together.
That's a great way to put it. They're essential for making sure the pilot has a clear picture of the airplane's orientation, even if the instruments are spread out across the cockpit.
Speaking of getting a clear picture, what about those colorful markings we often see on aircraft gauges? The homework specifically mentioned blue and green arcs. What's the story behind those?
Think of those markings as visual cues for the pilot. They're an immediate reference point for what's normal and what's not. Take that blue arc you sometimes see on an airspeed indicator that often shows the safe operating range when the flaps are extended.
Ah, so it's like a quick sanity check for the pilot. Am I in the blue? Good! Outside the blue, time to figure out why.
You got it. And those green arcs you mentioned, those usually show the normal operating range for whatever that gauge is measuring. Temperature, pressure, whatever it might be.
It sounds like aircraft instrument designers put a lot of thought into making this information clear and easy to understand, even when things are hectic in the cockpit.
Absolutely. They've got to make it as straightforward as possible for those split-second decisions.
Now, what happens if something's wrong with the instrument itself? How would a pilot even know if a gauge wasn't giving an accurate reading? The homework mentioned something called a slippage mark. Now, that sounds a little ominous.
It's definitely not something you want to ignore.
Hmm.
A slippage mark, usually a red radial line, is basically a warning sign that the instrument itself might not be reliable.
Oh, so it's like the instrument is waving a little red flag.
In a way, yeah. It could mean there's some internal wear and tear, like friction or, well, slippage, that's affecting the reading.
This is basically saying, hey, don't trust everything I'm telling you right now. Get me checked out.
Exactly. It's a critical safety feature, making sure pilots are aware of any potential issues with the information they're relying on.
It's amazing how many layers of safety are built into these systems. It's like every dial and gauge has a backup plan.
It's all about redundancy. You don't want a single point of failure causing a major issue. Aviation is all about anticipating what could go wrong.
Speaking of anticipating, we've covered a lot of ground when it comes to how pilots figure out their altitude.
Hmm.
We talked about pressure altitude, but I know our homework mentioned another type of altimeter, a radar altimeter. How does that one work? It seems like a completely different approach.
It is. Remember how we talked about standard day and how pressure altitude is all based on that standard? Well, a radar altimeter throws that out the window. It uses radio waves to directly measure how high the aircraft is above the ground.
So instead of relying on air pressure, it's like it has its own built-in measuring tape.
That's a great way to put it. It sends out those radio waves, they bounce back from the ground, and the altimeter measures how long it takes for that signal to return. Since we know how fast radio waves travel, it can calculate the distance, the altitude, incredibly accurately.
Wow, that is so clever. It makes sense why pilots would rely on that, especially during landing. All this talk about pressure has me thinking about something else. We've thrown around PSI and PSIA a bit, both ways of measuring pressure. What's the difference again? It's one of those things I always mix up.
It's easy to get them confused. Basically, it comes down to the reference point. PSIG, or pounds per square inch gauge, that's all about measuring pressure relative to the air around us, the atmospheric pressure. Like if you measure the pressure in your car tire, you're measuring how much higher it is than the air outside the tire.
Okay, so PSA is about the difference in pressure. What about PSIA?
PSIA stands for pounds per square inch absolute. Instead of using atmospheric pressure as a reference, it starts at 0, a perfect vacuum. So it tells you the total pressure in a system, regardless of what's going on around it.
So PSA is like saying, how much more pressure is there in this tire compared to the air outside? Well, PSIA is like saying, what's the total pressure in this system, period?
You got it. It's a subtle difference, but super important for making sure those calculations are accurate.
And I'm betting mixing those two up could have some, say, unintended consequences in the aviation world.
You could say that again. Imagine a mechanic using the wrong pressure reference when they're inflating a tire. Too much pressure, and, well, you know what happens to an overinflated tire? Too little, and it could fail during landing. Precision is key.
Talk about high stakes.
Yeah.
It really seems like every aspect of aviation, from those Borden tubes measuring fuel pressure to those color-coded arcs on the gauges, it all boils down to having the right information in the right format at the right time.
Absolutely. It's a testament to all the engineers, mechanics, the pilots, everyone who's worked to make this system as safe and reliable as it is. It's pretty amazing when you think about it.
It really is. We've just scratched the surface of this fascinating world of aviation electronics, but I have to say, I'm walking away with a whole new appreciation for what it takes to get those planes off the ground and back down safely. It's a delicate dance of science, engineering, and human skill.
Well said.
And you know what, listeners? There's a whole universe of instruments and systems we didn't even have time to touch on today. So here's something to ponder. We talked about altitude, speed, temperature, pressure. What other parameters do you think are crucial for pilots to keep an eye on during a flight? Think about navigation, communication, fuel consumption, electrical systems. There's a whole world out there to explore. So keep those minds curious, and we'll catch you next time as we continue to unravel the mysteries of this incredible field. Safe travels, everyone.